Okay, so we're going to be talking about basis and dimension today. So go ahead and open up section 2.7 and also get MATLAB open if you want to take notes and practice. All right, so I assume that you've paused the video and you're back now ready to roll. So before we can find a basis, let's talk about what one is. Okay, so if I have a subspace V, capital V, is a subspace of Rn, then a basis for V is a set of vectors, vector V sub 1, vector V sub 2, dot, 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 up to vector V sub m. I have this set of vectors such that the subspace V is equal to the span of those vectors, and the set of vectors is linearly independent. Okay, so there can't be any linear dependence. All the vectors have to be linearly independent, and their span has to cover V. It has to be equal to V, so that every single vector, and let's talk about what this word span means. We defined it before, but it means that any vector over here, any vector in V, can be written as a linear combination of these vectors. Okay, so that's what the span means. It means that I have a set of vectors which I can use to write a linear combination that's equal to any vector in the subspace. Okay, so it seems straightforward enough. Let's talk about how to do it. Okay, so if we have a set of vectors and we want to determine a basis for it, what do we do? Well, the first thing we do is we create a matrix whose columns are the vectors from that set. All right. So we create that matrix and we row reduce it all the way to RREF. All right. So reduced row echelon form. And why do we do that? We do that because we'll use the information from a couple of sections ago, or last section, to write a linear dependence relation. Okay, why? Okay, well, it turns out that depending on how many pivots we have and whether or not all of this is possible, then we're going to have a basis for the subspace spanned by the set of vectors. Okay, so this is the example from the section in the online notes. All right, so we have these three vectors. V sub 1 is -1, -4, 1, and so forth. You see V2 and vector V sub 3. You'll see that those are, in fact, what we have. And let me jump over to MATLAB. Okay, so again, I just have the list of vectors right here. Okay, and I've copied this from the online MATLAB notes. I just copied this in, and so we have the matrix M. I was just running the section, so we have everything in the computer. All right. And notice that, in fact, the matrix has as its columns the correct vectors. So the first column, -1, -4, 1, is V1, and -6, -26 is V2, and so forth. You can see V3 is also correct. Okay, and what do we do? Well, oh, and by the way, this is just for later. We can use this. Let me explain, right? So the vector V1 is the first column of M. So remember, this notation is row, comma, column. So for row, we use the colon operator, which is all the rows, and comma, column 1. So it's basically everything in column 1. So that gives us the vector V1. And so on for the vector V2. This is specifying column 2. And this is specifying column 3 for V3. Okay. So, but the matrix M is what we need, and we want to row reduce it. So let's run this. Okay. And remember that we have a row of zeros here. So we have two pivots. And just to refresh your memory, two pivots means we only have two of the vectors that are linearly independent. So in other words, we're going to have the spanning space, the space that these vectors span, is only two-dimensional. So a basis of just two vectors will work. And it turns out that I can, if I think of this as an augmented matrix, right, that this right here, these are the coefficients of the linear dependence relation. Okay, so let me get rid of the ink and scroll up just a little bit. All right, so this is what we're talking about, right? The equal sign is here. So we're saying, hey, the value for C1, right, that we need is -1/2. And the value for C2 that we need is 3/4. Okay, and then of course there's all zeros on the bottom, which makes sense. And getting rid of the ink, we can see that this means that this vector, right, these are the coefficients, right? Our coefficient C1 equals -1/2, our coefficient C2 equals 3/4, and our coefficient C3 equals 0. Okay, that's all good. And so we end up with this nice equation. And I'm sorry, I should have written C's in here. No, I guess I shouldn't have. Let me see what vectors we're looking at. Yeah, I probably should have used. So these values are the C's. The -1/2 and 3/4 are the C's. So I probably should have used V's instead of X's here, but this is what's true. The vector V3 is equal to 1/2 times the vector V1 plus 3/4 times the vector V2. Okay, and how do we know that? Well, again, the coefficients are all right here. And just to remind you, that is the last column of the row-reduced matrix. Okay, so getting rid of the ink, let's jump down and see how we can test this. Okay, so first thing to know is that the double equal sign is a Boolean operator, which basically says, is this true or false? And if the equal sign is true, then we'll get all ones. And if the equal sign is false, we'll get all zeros. Okay, so let's do this, right? So I've created these vectors, v1, v2, v3, and right, that was, sorry, right above the row reducing, right? That's this part. That's why we have them, right? So we have these vectors, and we're going to see if this equation is correct. How are we going to do that? Well, v3 equals -1/2 times v1. Again, I should have used v instead of x up here. Sorry about that. Plus the 3/4 v2. Okay, boom. And it says logical array. Why? Because it is a Boolean operator, right? It's either true or false. And the ones mean that it's all true. Again, if we'd had a 1 and 2 zeros, that means that parts were true, but parts were not. But we got all ones, which means everything is true. So let's just take the right-hand side here and evaluate it. And you see that the answer, when I do -1/2 times v1 plus 3/4 times v2, I do get -4, -13, 4, which, if you remember, is exactly what we were going for, right? -4, -13, 4 is exactly what v3 is equal to. Okay? So this equal sign gives it to us, and then we can actually see it evaluating to the right thing. Here's v3. So we in fact have, if I had used v's here, we in fact have the correct linear combination of the vectors x1 and x2 that produce, v1 and v2 that produce the vector v3. Okay, so we have a basis for the subspace that these vectors of v span. Okay, it's a two-dimensional subspace. Why? Because I only have two vectors, right? It can only be a two-dimensional subspace because I don't have a third vector over here in the linear combination, right? So it's a two-dimensional subspace. And let's do another example. All right, jumping back to our example, right? Find a basis for the set of vectors. Okay, so that's interesting. But the question is, are they linearly independent? And let me throw this out. They live in R4 and there's 5 of them. So my guess is they're not linearly independent. If we have 5 vectors, they could span R5 if they were linearly independent. 5 vectors linearly independent would span R5 or could span R5. And so these are only these vectors live in R4. Do they span R4? We don't know. We know there's some linear dependence. So we're going to have to take a look. So the first thing we're going to do is we're going to create a matrix R whose columns are the above vectors. And you can pause the video and double check that they are in fact the right vectors. Let's go back to work in MATLAB. Okay, so I have just copied this out of the notes, the online notes. And so we have the vector R in there. And what I'm going to do is I'm going to row reduce R. Okay, and so since I've run the section, it's been run. And the thing I want you to notice is there are 3 pivots, right? So there's a pivot in the top left, there's a pivot in the second column, and there's not a pivot here until the 5th column. Okay, so there are 3 pivots. And what does this mean? This means that where the pivots are, those vectors in the original vectors, u sub 1, u sub 2, and u sub 5, they're the ones that are linearly independent. And so those are the ones that span the set of vectors, and so that's the basis. The original vectors, u sub 1, u sub 2, and u sub 5. Sorry, get rid of the ink. And so what do we have? Well, if we only have 3 vectors, right, 3 vectors in the basis, then at most we're spanning a 3-dimensional subspace. All right, 3-dimensional subspace. And let's jump back to MATLAB for just a moment. Right, so these 2 vectors can be written as linear combinations of u1, u2, and u5. Okay, so I want to be clear, we have 3 pivots, 1, 2, and 3. So we have a 3-dimensional subspace, right, that is spanned by these vectors, and a basis for that span is the vectors u sub 1, u sub 2, and u sub 5. All right, we'll talk a little bit more about bases and coordinate systems in the next lesson.